Okay, so what we're going to do is a couple examples. So this is one that comes straight out of Reddy's book, example 9.2, and what it talks about is interpolation functions for a special type of quadrilateral element. So in this element you have 5 nodes, one's on the 4 corners and then one in the center. And the coordinate system we're using is the local coordinate eta and z. And what he asks is, given these 5 interpolation functions, so you need 5 to represent all 5 nodes. Here are your answers. So I'm not writing them all down, but he gives all of these and he wants you to prove why this is equal to these things. So we're going to go through and do this one, and the other 5 follow an identical manner. So first what we do is we propose that a complete polynomial is given in this form. So you have these unknown constants ai, bi, ci, di, and ei as functions of linear and quadratic and constant terms in terms of z and eta. And I is for I goes 1 to 5, so you're going to have constants 1 to 5. And here's what we do. So for psi1, at node 1, this interpolation function equals 1, and this same interpolation function equals 0 on the other 4 nodes, right? So we just plug in values. Remember, this is a local coordinate system, so it ranges plus or minus 1, the top and bottom. So we're just plugging in values for z and eta. You equate it to 0 or 1, and now you have a matrix set of equations. So all we have to do is invert this, and you can solve for a1 through e1. Determinant is 32. If you integrate, or you take the inverse of a, you get these values, and that should be the same as what was given for psi1. So you'll go through, do the same thing for psi 2, 3, 4 to 5, and that'll give you the other interpolation functions. Next problem, so 9.8. In this problem it asks to determine Jacobian matrix and the transformation equations for the following element. So in this element you have some numbers for a parallel 4-node element, or basically a geometry of a quadrilateral element in x and y space. And one of the things that we will, if not already, have talked about in class is we can write our coordinates x and y in terms of the local z and eta coordinates. So here are your values xj, which will most likely be, let's say, I believe in this problem, yes, so in this problem we use 4-node element. Okay, so m is going to be 4, so you're going to have 4 values for xj and yj. So you have to figure out what are my values. Here it's 0, here x is 10, y is 0, and etc. based on geometry. So we go through and figure out what those are, and then you're left with plugging in values for the interpolation functions. So first thing we have to do is figure out what those interpolation functions are for this given problem. So very similar to the last problem, except here you have 4 nodes. We have C1, 2, 3, and 4. These are my unknowns. And again, remember, psi1 is going to be 1 at its node 1, and it's 0 at nodes 2, 3, and 4. So that's why we have psi1 is 0 on these 3 points, right? So put this into a matrix equation. We get this form. Here are unknowns, so we take the inverse and we solve, and we get this form for psi1. Do the same thing for psi2, except now this is the node where that interpolation function is 1, the other 3 are 0. Invert, you get this form. Do the same thing on psi 3, only difference is here's your 1, other 3 are 0. Psi 4, these are 0, bottom one, this is node 4, so that's going to be 1. So this gives you numerical values for all 4 of your interpolation functions. And now we go back and plug in values for x and y. So remember, to get x and y, we're going to go through, plug in these values and do a summation on psi 1, 2, 3, and 4. And what all this is leading to is a relation between x and y and c and zeta, right? So here's our value, or here's our relation for x, the Jacobian. Right, so here's our definition of the Jacobian. It's partial derivatives with respect to both coordinates. When we take these derivatives, remember, these are constants, so you're only taking derivatives on the interpolation functions. So you do this for the 4 terms. If you want to write this out in matrix form, you can do it like this. It gives you the same thing. You multiplying and doing a summation, you get this. Notice, same thing up here, right? 5 square root of 3, and 5. So if you take the determinant of this matrix, you get 25, and it's greater than 0, which means it'll be positive definite, and you can invert it to solve problems. And that concludes these examples.